Hi everyone, in this video we'll be learning how to use the list processing algorithm. In general, what this algorithm does is takes a list of tasks that need to be scheduled and it produces a schedule. And mathematically, as far as structures go, these are our inputs. We have a digraph, which is a graphical representation of the tasks, a priority list, which tells us which tasks have the highest priority and then which have the lowest priority, and we have to know the number of processors. So those three things have to be given to you in order to run the list processing algorithm. And then the output is the schedule itself. And the schedule will have the optimal time, which means the shortest total amount of time that it takes to schedule all these tasks on this number of processors given this priority list. So here are the steps to the algorithm, and we'll actually run through this. So this will make a lot more sense, I think, when you see an example, but these are the general steps. So the first thing you do is you go to your priority list, and in correspondence with the digraph, you decide which tasks are ready, and then you circle all the tasks that are ready. That indicates that they can be put in the schedule at the current time. So then you assign tasks, and the way you do that is assign the first ready task, and this word first here means first in the priority list. So not the lowest number necessarily, but whichever one comes first in the priority list. It has the highest priority. And then we assign that to the first available processor. This use of the word first means lowest number processor. That's how we break ties. If we have multiple available processors, we just go with the lowest number. And then you mark that task as assigned. Typically when I run the algorithm, I just put an X through the task. That's in the priority list. And then you just repeat this process as tasks become completed. So you move through time, and every time a task is completed, you remove it from the digraph because it's no longer affecting the others, and you just keep repeating step one, and then run through the cycle until all tasks are scheduled, and then you're done. So let's look at this example. This is a digraph at the top. This digraph represents a bunch of tasks that need scheduled. In fact, there are 12 tasks. The subscripts are indicating the task numbers, and the parenthetical numbers represent the times. So for example, this is task 1, and it takes 5 units of time to complete. This is task 9, and it takes 3 units of time to complete. And this is the last task, task 12. So our priority list is given to us, and our number of processors are given to us. This tells us that we have 2 processors, which is denoted here. And then this priority list starts with T1 and then T2, 5, 10, 12, 11, 9, 8, 7, 6, 4, and 3. So the highest priority task is 1, the lowest priority is 3, and then everything else is lined up in between. So we'll just actually run the algorithm. Okay, so remember what we do first is we look at the digraph and notice that, just for example, task 11, that requires task 2 and 3 to be done before it can start. And that's indicated by these arrows that are going from 2 and 3 to 11. So right here at the beginning at time 0, nothing has been scheduled, which means that task 11 is not ready. So I'm not going to circle it. But tasks 2, 3, 5, and 6 are ready because they have nothing out here before them. So I'm going to circle those. 2, 3, 5, and 6. And them being circled indicates that they're ready. They can be scheduled right now. So that's step 1 of the algorithm from the previous page. Step 2 is assign the first ready task to the first available processor. So I'm going to scan across the priority list from highest to lowest, and the first ready task I come to is task 2. So I will take task 2 and schedule it on the first available processor, which is here. processor 1. And task 2, that's now been scheduled, it takes 7 units of time, so I'll just kind of take my best guess and say it's going to run to out there. That's 7 units of time. So task 2 is taking up this block. Task 2 is not currently finished running because we have a processor that's available back here at time 0. And so I'm going to go back to time 0 while task 2 is running and think about what I can schedule. There's nothing new that I can circle because nothing has been completed yet, so there are no updates to be made. So at time 0 on processor 2, the first available task is 5, so I'll schedule it. And up here, task 5 we can see takes 4 units of time, so that will run out to here. That's task 5. So this is 4 units of time. And then task 5 has been scheduled. So then I just keep going ahead in time until something is completed. So that means time 4. That's the first thing, that's the first time that something is completed. So task 5 is done, is completed, which means that I get to remove it from the digraph. So if this were in pencil, I would just erase it, but scribbling it out indicates that task 5 is done. Therefore, it's removed. It doesn't have to be considered anymore. And so I'll just check, is there anything up here that can be updated? The only thing affected was task 1, but it still has things that need to be done before it. So I can't circle it yet because it's not ready. So there are no updates to make at this time. Alright, so I go to the first available processor, which is processor 2, here at time 4. And I scan the ready tasks, and task 6 is ready. Task 6 takes 2 units of time, so that'll take me out here to time 6. And I'm going to schedule task 6 from time 4 to time 6 on processor 2. So now it's scheduled. So I've crossed it out because it's been scheduled. And I just keep repeating this process. So the first available time is 6. And task 6 is done. So I'm going to remove it. Again, no updates to make because task 1 still has something that needs to be done before it can start. And so at time 6 on processor 2, I'm going to scan across, and the first and only ready task I come to is task 3. So I will schedule it. And task 3 takes 4 units of time. So that started at time 6, and it takes 4, so it's going to run to time 10. And then 3 has been scheduled. So then the first available time is 7, and now 2 is done. So I'll remove it. And now I have an update to make. Task 12 is ready because 2 is finished, and that's the only thing that had to finish before task 12 could run. So I'm going to circle 12. 11 still has something that needs to run before it. Because remember, at time 7, 3 is still running, so it's not finished yet. Alright, so at time 7, I'm going to schedule the first available task. The only one is 12, so I'll schedule task 12. And task 12 takes 6 units of time, which is going to take us out here to 13. And it's scheduled, so I'll cross it off. So then I'll go back here to time 10. Task 3 is done. So I actually have 2 updates. 11 and 1 are both ready. So they get circled. And then at time 10, I'm going to schedule the first available, which is task 1. And task 1 takes 5 units of time. So that'll take us out here to 15. Started at 10. And task 1 has been scheduled. So then my first available processor is processor 1 at time 13, so 12 is done. Remove it. No updates to make, so I'll scan across, and 11 is the first thing that I can schedule. And that takes 1 unit of time, so that's going to take me here to 14. That's task 11. So it's been scheduled. And then actually processor 1 is the first available because that only took 1 unit of time. So we're at time 14, 11's done. We have 1 update to make, 4 is now ready. And we're at time 14. Remember 1 is still running here, so we haven't taken that away. So we scan across, and 4 is the first thing that I come to that's ready. Task 4 takes 2 units of time, so that's going to take us here to 16. That's task 4. It's been scheduled. And then my first available time is 15, and that's processor 2. So task 1 is done. Get rid of it. 2 updates to make. 7 and 8 are now ready. So I'm going to circle them. And at time 15, I'm going to scan, and the first available task, first ready task, is task 8. So I'm going to schedule that. And task 8 takes 7 units of time. Started at 15, so it's going to go out here to 22. So it's out, it's running until 22. 8 has been scheduled. First available time is 16, so 4 is now done. So I have 1 update, 9 is ready. So I'll scan across. 9 is the first thing, in fact, that I come to. So here's task 9. And that takes us to 19. Because task 9 takes 3 units of time. Which means that processor 1 is the first available now again. And so 9 is done, but there's nothing to cross off, so I just don't update anything. So no updates to make, nothing to circle. Alright, so I'm going to scan task 7. That's the first one that I come to. And that takes 10 units of time, which is going to take us out here to 29. That's task 7, it's been scheduled. At time 22, 8 is done, but 10 still requires 7 to be done, so there's no updates to make. So at time 22, I'm going to scan, and notice here, this is the first time that we have an open processor, but nothing is available to schedule, which just means that it's idle, it can't do anything. So we're going to have to push this time out until something completes, and that means we got to go out here to 29, and this is idle time. That's just time that processor 2 is not doing anything. It has to wait. There's nothing it can schedule. Alright, so now I have kind of a fresh slate. So now at time 29 I have 2 processors available, which means that I just picked the lowest number, which is processor 1. And so at this point, task 7 is done, so I'm going to get rid of it. Which means I can update, and 10 is now ready. And that's the only update, so I scan across task 10, I can schedule, and it takes 3 units of time, so that's going to take me to 32. And actually that's the last thing I need to schedule, which means that I'm essentially done. So technically here is more idle time for processor 2, and that's okay. And then the schedule is complete, so this is the output of the list processing algorithm. It's the schedule itself. And the runtime, which is the optimal time, is 32. That's the total time it takes to run all of these tasks on 2 processors with this priority list. And that completes the list processing algorithm example.